They named it, they measured it, and then they sat back and stared at their data in silence, because what the numbers were telling them made no sense. A star so impossibly vast that it violated the theoretical ceiling astronomers had spent decades calculating. A ceiling that was supposed to be unbreakable. A ceiling that said no star could grow past a certain size without tearing itself apart. And yet there it was, sitting in the data, patient, agent, refusing to obey the laws that every other star in the known universe had followed without question. Before we get to that star, you need to understand something. The night sky you've looked at your entire life has been deceiving you. Every single one of those cold pinprick lights is a nuclear furnace, on a scale your brain was never built to process. The difference between the smallest and the largest star we've ever found is so extreme that if you tried to walk from one side of the largest one to the other at highway speed, 100 kilometers per highway speed, you would die of old age before you completed the journey. Your children would die, their children would die, and you'd still have centuries of star left to cross. Today we're going to meet the 5 most extreme stellar objects ever discovered by human beings. Each one bigger, stranger, and more unsettling than the last. And by the time we reach number 1, you will never look at the night sky the same way again. Before we go further, you need one piece of scientific vocabulary, one number that makes everything else make sense. The sun's radius, the distance from its center to its surface, is approximately 6,986,000 kilometers. Astronomers call this one solar radius. It's the ruler they use when measuring stellar giants, because saying this star is 483 trillion kilometers wide tells the human mind absolutely nothing. Saying this star is 1,700 times the size of our sun at least gives you a foothold. Here's your foothold. Our sun is already enormous by human standards. It contains 1.3 million Earths. Its surface could swallow every planet in our solar system and still have room left over. If you replace the sun with the largest star on this list, the closest thing to Earth, the asteroid belt, the orbit of Jupiter, the orbit of Saturn would all cease to exist. They'd be inside the star, submerged, dissolved into plasma. Keep that in mind as we begin. 500 light years from Earth, in the constellation Scorpius, there is a star so red and so bright that ancient Greek astronomers named it Antares, literally rival of Mars, because its deep crimson glow competed with the red planet in the night sky. You've probably seen it without realizing it. On a clear summer night in the southern hemisphere, or low on the horizon in the northern, it burns like a dying ember against the black. Antares is classified as a red supergiant. Its surface temperature has cooled to around 3,400 Kelvin hot by any human standard, but cold for a star. And it's that relative coolness that gives it that distinctive blood red color. The physics is simple. Hotter stars blaze blue-white. Cooler stars smolder red. Antares is smoldering. In terms of size, Antares measures somewhere between 700 and 800 solar radii. Drop it into our solar system, and its surface would extend past the orbit of Mars. Earth would be a memory, a deep space memory, swallowed without ceremony inside a star that from the outside looks like nothing more than a faint rusty dot in the sky. But here's the part that should unsettle you. Antares isn't just large, it's unstable in a way that carries specific consequences for everything nearby. The star is pulsating, rhythmically swelling and contracting over years-long cycles. Its outer layer is pushed outward by radiation pressure and then pulled back by gravity. Each pulse sends shock waves through the star's extended atmosphere. Each pulse strips more mass away into space. Antares is slowly bleeding out. And when the luck, the bleeding finding the first one, and the balance between outward radiation and inward gravity finally collapses, the result would be a quiet fade. It will be a supernova visible from Earth in daylight. Astronomers don't know exactly when. It could be tomorrow. It could be 100,000 years from now. But the countdown is running, and Antares is only number 5. For decades, VY Canis Majoris held the title, the largest star known to humanity, a red hypergiant sitting 3,900 light-years away in the constellation Canis Major, far enough that you need a mid-range telescope to spot it, but close enough that astronomers had been studying it with obsessive detail for over a century, and what they found made even experienced astrophysicists pause. At its peak estimates, VY Canis Majoris measured approximately 1,440 solar radii. With that in terms you can feel, if you replaced our Sun with VY Canis Majoris, its outer atmosphere would extend past the orbit of Saturn, not Jupiter, Saturn, the sixth planet from the Sun, 1.4 billion kilometers from where you're sitting, would be embedded inside this star's outer layers. The four inner planets, the asteroid belt, Jupiter and all its moons, gone, absorbed, existing somewhere inside a roiling, turbulent mass of plasma and magnetic chaos. But VY Canis Majoris isn't just enormous. It's violent in a way that makes it one of the most extreme environments in the known galaxy. The star loses mass at a rate that defies easy comprehension. Every year, it sheds enough material to build dozens of Jupiters, blasting it outward in asymmetric jets and massive eruptions that create a complex nebula of expelled gas and dust surrounding the star. Astronomers studying this debris field have found evidence of individual eruptions, single events that released more mass than our entire Sun contains in its outer layers. The star isn't just bleeding, it's throwing pieces of itself into space like a wounded animal. What drives this? A combination of extreme luminosity and magnetic turbulence. VY Canis Majoris radiates somewhere around 300,000 times more energy than our Sun every second. That radiation pressure from inside is constantly fighting to push the star apart. The outer layers, barely held together by gravity, are being hammered from below by a nuclear furnace of almost incomprehensible power. Here's what that means in practical terms. VY Canis Majoris is destroying itself. Slowly, spectacularly, and when it finally runs out of fuel, when the core collapses under its own weight, the supernova explosion that follows will be so powerful that astronomers have a separate category for it, a hypernova, an event so energetic that it briefly outshines entire galaxies. VY Canis Majoris is not just a big star, it's a catastrophe in slow motion, an event that hasn't happened yet but is already written into the physics of the star. And it's only number 4. Now we leave the Milky Way. The next star on this list doesn't live in our galaxy. It lives in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way, visible to the naked eye only from the southern hemisphere as a faint, irregular smudge of light. The Large Magellanic Cloud is roughly 160,000 light-years away, which means when you look at it, you're seeing light that left before modern humans existed. Inside that distant galaxy, there's a star called WHE6 Tor, discovered in the late 20th century and refined through subsequent observations. Bob's classified as a red hypergiant, one of the rarest and most extreme stellar categories in existence. Current measurements place it at approximately 1,500 to 1,730 solar radii, though estimates vary due to the difficulty of measuring a star at such extreme distance with precision. What makes WOHD 64 particularly interesting is not just its size, it's what surrounds it. The star is embedded inside a torus, a donut-shaped cloud of gas and dust that it has ejected from its own outer layers over thousands of years. This torus is so dense and so complete that it partially obscures the star itself, making precise measurement extraordinarily difficult. Astronomers are essentially trying to measure the star through a wall of its own shed skin. What they can measure is the luminosity, approximately 280,000 times that of the Sun, pouring out of a star that is already in the advanced stages of stellar decay, losing mass rapidly, likely within the final 100,000 years of its life, a blink of an eye in cosmic time. There's something philosophically striking about WHD 64 that astronomers rarely talk about. Because it's 160,000 light-years away, The light reaching our telescopes today left that star 160,000 years ago. We have no idea what G64 looks like right now. For all we know, it has already exploded. The hypernova may have already happened, already sent a shockwave of energy tearing through the Large Magellanic Cloud, already illuminated surrounding gas clouds in colors that won't reach our telescopes for another 100,000 years. We are watching a ghost, a stellar ghost, sending us light from a past that no longer exists. WOCH G64 is number 3, and we're getting closer to something that shouldn't be possible. Until recently, this was the one, the undisputed champion, the star that held the record for the largest known stellar object in the universe, UY Scuti, a red supergiant in the constellation Scutum, approximately 5,100 light-years from Earth, discovered by German astronomers in the 19th century and largely ignored for over 100 years before modern instruments revealed what it actually was. UY Scuti has a radius of approximately 1,078 solar radii. Some measurements have pushed that estimate even higher. Its volume is so extreme that fitting our sun inside UY Scuti would be like fitting a marble inside a hot air balloon, except the margin is even more absurd than that analogy suggests. You could fit approximately 5 billion suns inside the volume of UY Scuti. 5 billion. Our sun, which already contains 1.3 million Earths, becomes statistically meaningless by comparison. Place UY Scuti at the center of our solar system, and its surface extends past the orbit of Jupiter, not to Jupiter, past it. The largest planet in our solar system, the gravitational anchor that shaped the formation of everything in the inner solar system, would be swallowed whole and wouldn't even disturb the star's outer layers noticeably. UY Scuti also demonstrates something important about the extreme end of stellar physics, something that sets up the final entry on this list perfectly. Massive stars like UY Scuti don't live long. The physics of stellar evolution is cruelly counterintuitive. The more massive a star, the faster it burns through its fuel. Our sun will live for roughly 10 billion years. UY Scuti, despite having vastly more fuel to burn, will live for only a few million years because it burns that fuel at a rate millions of times faster. It's not a campfire, it's a detonation in slow motion. At its current luminosity, roughly 340,000 times that of the sun, UY Scuti is consuming itself at a rate that means its time is almost up in cosmic terms. The star is losing mass constantly, its outer layers being pushed away by radiation pressure, its core slowly running low on the hydrogen that has sustained it. When the hydrogen runs out, the core will begin fusing helium, then carbon, then neon, then oxygen, then silicon. Each new fuel source burns faster than the last. The final stages of a massive star's life compress millions of years into thousands. And the end, always, is catastrophic. UY Scuti is not just the second largest star we know of. It is a masterclass in the relationship between mass and time. The bigger they are, the faster they die. And the deaths, when they come, rewrite the local universe. But UY Scuti is second now, because something was found that changed everything. Here's what the theory said. For decades, stellar physicists worked within a boundary called the Eddington luminosity limit, a theoretical ceiling on how bright and therefore how massive and large a star could become before its own radiation. Pressure would tear it apart. When a star gets too luminous, the outward pressure of its own light becomes stronger than gravity's inward pull. The outer layers get blasted away faster than new mass can accumulate. The star effectively self-destructs before it can grow further. This limit was supposed to keep stellar sizes in check. It was one of the most robust projections in stellar astrophysics. And then someone pointed a telescope at a star cluster in Scutum and found something that made them question whether the limit applied the way everyone assumed. Stephenson 288, also designated Saint 218 in the literature. A red supergiant sitting approximately 19,600 light-years from Earth, embedded in a stellar cluster called Stephenson II, a dense collection of massive stars in the plane of the Milky Way, first catalogued by American astronomer Charles Bruce Stephenson in 1990. Recent measurements, refined through near-infrared observations and careful parallax analysis, have placed the radius of Stephenson 288 at approximately 2,150 solar radii. Some analyses have suggested it could be as large as 2,158. Let that number sit for a moment. 2,150 times the radius of our Sun. If you place Stephenson 288 at the center of our solar system, its surface would extend past the orbit of Saturn and push toward Uranus. 6 of the 8 planets would cease to exist as separate objects. They would be inside the star. The asteroid belt, Jupiter with all its moons, Saturn with all its rings, gone. Dissolve. The surface of this star would sit somewhere between Saturn and Uranus, meaning from Uranus. If you could stand there, this star would fill the entire sky in every direction, edge to edge, horizon to horizon, nothing but burning plasma as far as any telescope could see. The light travel time from one side of Stephenson 288 to the other is approximately 8.5 hours. Light, traveling at 300,000 kilometers per second, would need 8.5 hours to cross the star. For context, light from the Sun reaches Earth in 8 minutes. A single diameter of Stephenson 218 represents more than an hour of light travel compared to the Earth-Sun distance. And here's the part that genuinely troubled the astronomers who measured it. Stephenson 218 doesn't obviously violate the Eddington limit, but it pushes right up against the theoretical boundary in ways that demand explanation. Its luminosity is measured at approximately 90,000 times that of the Sun, which is actually lower than many smaller hypergiants. This is unusual. The star is massive and enormous, but it's not as blindingly luminous as its size might suggest, which means the relationship between its mass, its size, and its energy output doesn't fit neatly into the standard models. Astronomers have proposed explanations. Perhaps the star has lost so much mass from its outer layers to stellar winds that what we're measuring is an extremely extended, diffuse atmosphere, a bloated envelope that makes the star appear geometrically large while not reflecting the full nuclear fury of its core. Perhaps the star is in a transitional phase, having swollen rapidly after a change in its internal fusion process, and the outer layers haven't yet had time to respond to the new equilibrium. Perhaps there are magnetic field structures or rotation effects at play that are captured in the simplified models. None of these explanations are fully satisfying. None of them are definitive. The honest scientific answer is that Stephenson 218 is not fully understood. It is a data point that challenges the framework rather than confirming it. That is the mark of a genuinely important discovery, not one that fits neatly into what we already knew, one that forces us to ask better questions. Here's what you need to take with you from all of this. Every single one of these stars, Antares, VY Canis Majoris, WHD64, UY Scuti, Stephenson 218, exists right now, or existed until very recently, within the same galaxy or within its immediate gravitational neighbor. They are local, by cosmic standards, they are our neighbors, and they are doing things that physics can barely account for. The universe is not a calm, static collection of lights. It is a violent, ongoing process. Stars are being born and dying constantly. Supernovae are happening right now, somewhere in the observable universe, at a rate of roughly 1 per second across all the galaxies we can detect. The largest stellar objects we know of are all in the final stages of their lives, burning their last fuel with disparate brightness, shedding mass at catastrophic rates, building toward endings that will reshape the space around them for thousands of light years. And here's the thing that should stay with you. We have surveyed only a fraction of the observable universe. The instruments we use to find Stephenson 218 are powerful but not omniscient. There are approximately 2 trillion galaxies in the observable universe. We have detailed information on a handful. The stars we've measured in any real depth are a sample so small relative to the total stellar population of the cosmos that calling it a drop in the ocean would be an astronomical overstatement. Stephenson 2.8 shocked astronomers with a radius of 2,150 solar radii. But the universe does not run on human expectation. Somewhere in the billions of uncharted galaxies, in star-forming regions we haven't pointed a telescope at, in clusters we haven't catalogued, there are almost certainly stars that make Stephenson 2.18 look the way Antares looks compared to our sun. We haven't found them yet. The record won't stand forever. It never does in astronomy. And when the next one is found, when something pushes the boundary even further, the question it will raise is the same one Stephenson 2.8 already asks. How big can a star actually get before the universe's own laws refuse to allow it? We don't have that answer yet. But we're looking.